All right, so today we're diving into something pretty neat that you brought to our attention.
Okay.
It's all about how scientists turn microbes into like these little overachievers,
Hmm.
getting them to produce way more of these valuable substances like amino acids,
Right.
those building blocks of proteins
Yeah.
or even nucleotides, those components of our DNA and stuff.
Uh-huh.
And the thing is, from what I've gathered from these sources you sent over,
Okay.
these microbes are already pretty good at regulating themselves. Like they don't want to waste energy making more than they need.
Yeah, that's right. It's like a built-in efficiency thing.
So how do the scientists overcome that then?
Well, it's a lot like think of it as a factory that knows when to slow down production if the warehouse is full.
Gotcha.
Microbes have this similar control system, and it's often through this thing we call feedback regulation.
Okay.
So the end product of a pathway, it actually signals back to an earlier step to basically hit the brakes on production.
Like a stop sign.
Exactly. So say you've got amino acid A. When there's enough of it, it can actually jam the machinery that makes more of A.
Oh, wow.
That's called inhibition.
Hey,
Or it can even tell the cell, hey, stop reading the blueprints to make that machinery altogether, and that's repression.
so it's like a multi-level stop sign almost.
Exactly. It's pretty sophisticated.
That's so cool.
Yeah.
So the microbe gets the message like enough lysine
Yeah.
and it just stops making it.
Right.
But what if we want like a ton of lysine or threonine or some other useful molecule?
Well, that's where things get really interesting.
Yeah.
That's where this super clever strategy called analog resistance selection comes in.
Okay, I'm intrigued.
It's all over your materials, and it's really a central point to how we manipulate these systems.
So that's what we're going to try to break down in this deep dive, right?
Exactly. We want to understand how this analog resistance trick helps scientists find those microbial mutants that basically miss the stop signal. And because they miss it, they just keep overproducing, which is what we want.
Right.
It's really ingenious.
So, okay, let's start with the basics. What exactly are these analogs in this context?
Okay, so analogs are basically like molecular mimics.
Okay.
They're compounds that are similar enough to the natural metabolite, let's say an amino acid.
Huh.
They can actually bind to the microbe's regulatory system
Right.
and trigger that feedback mechanism, that warehouse full signal.
Oh, I see.
But the key difference here is that the microbe can't actually use these analogs.
Ah, so they're like decoys.
Exactly. They're just there to send a false alarm.
And this false alarm can be toxic, right?
Yeah, you got it.
Like a faulty smoke detector that just won't shut up and stops any real work from happening.
Precisely. That's a great analogy.
So scientists are basically using these toxic analogs to mess with the microbes.
In a way, yes. So when a normal microbe encounters one of these analogs,
Uh-huh.
it gets tricked into thinking there's already a ton of the desired metabolite,
Okay.
which halts production.
Right.
But since the analog's useless to the cell, it can't actually use it.
So it's like tricking it into starving itself, basically.
Yeah, essentially it can't multiply.
So how do we find the overachievers in this scenario? The ones that keep producing.
Okay, so that's where mutagenesis comes in.
Okay.
It's basically introducing random typos into the microbe's instruction manual, its DNA. And this creates a whole bunch of mutants, a diverse population.
Okay.
And then we apply what we call selection pressure.
Mhm.
So we grow this motley crew of mutants on a special growth medium.
All right.
And this medium contains the toxic analog.
So it's like a survival of the fittest test.
It's microbial natural selection in action.
Only the strong survive.
Well, only the resistant ones.
Right.
Only the ones that can handle the analog can survive and reproduce.
And that resistance is often because their brake pedal, that feedback regulation is kind of faulty, right?
Precisely, it's no longer working as it should.
The factory just keeps churning out product.
That's the idea. The survivors are likely to have a reduced sensitivity to that feedback signal. Their systems don't respond as strongly to the analog anymore. And often this carries over to the actual end product, too.
So they just keep producing even when they shouldn't.
Exactly. We call it a deregulated phenotype, meaning their production's not really controlled anymore, and that leads to overproduction.
So I've got the why, but what are the actual steps scientists take to find these overproducers using this analog resistance thing?
All right, so it's a multi-stage process.
Lay on me.
First, you got to induce mutagenesis to get that genetic variation, shake things up a bit.
Right, creating those mutants.
Then you plate these microbes on a dish with the toxic analog.
Uh-huh.
That's the test.
Okay.
Then you got to pick the colonies that actually grow the survivors.
The winners.
Exactly, your potential winners at least.
Oh.
But it's not over yet.
Right.
You got to retest these survivors to make sure they're truly resistant and not just lucky.
A double check?
Exactly. And then the crucial part, you screen these resistant mutants to see which ones are actually overproducing the metabolite we're after.
Because not every resistant one will be a super producer, right?
Right. Some might just be good at surviving the analog, but not necessarily overproducing.
That makes sense.
And finally, you got to analyze the best ones, the top performers at a molecular level.
To understand why they're such overachievers.
Exactly. It's about figuring out the mechanism behind their overproduction.
So these sources you gave me, they have some pretty interesting examples of these analogs.
Oh, yeah, for sure.
Like for lysine, there's this one called diaminoethylcysteine, or DAEC for short.
Uh-huh.
It interferes with a key regulatory enzyme.
Right?
And what's amazing is how this tiny change in the DAC molecule can act like this powerful switch.
Yeah, it highlights just how sensitive these biological systems are.
It's really remarkable.
Absolutely. So DAEC, it basically mimics lysine and it inhibits aspartokinase, which is a crucial control point early on in lysine synthesis.
So by selecting for microbes that are resistant to DAEC,
You often find the ones with a less sensitive aspartokinase.
leading to more lysine.
Exactly, and we see similar strategies for other metabolites too, like methylthreonine for threonine, 5-methyltryptophan for tryptophan,
Okay.
fluorphenylalanine for phenylalanine and tyrosine.
Wow, it's like a whole arsenal of molecular tricks.
And for nucleotide production, you have analogs like 8-azaguanine for purines and 5-fluorosyl for pyrimidines.
So it's all about finding the right imposter for the job.
Precisely.
So for our listener, what makes this analog resistance method so appealing? Why do scientists like it?
Well, for one, it's super direct and efficient.
Mm-hmm.
You get the mutants you want without messing around.
Right.
Plus, it's generally pretty simple and cost-effective.
Makes sense.
And often you end up with mutants that are like seriously impressive overproducers.
But it's not perfect, right? There must be
Huh.
some limitations.
Oh, yeah, for sure. No method's perfect.
What are some of the drawbacks?
Well, first off, we don't have suitable analogs for every pathway.
So it's not a universal solution.
Unfortunately not. And also, resistance doesn't always equal a defect in feedback regulation.
Oh, right, because microbes are tricky.
Exactly. They're masters of adaptation, always finding new ways to overcome challenges.
Right.
It's something we always got to consider.
So they might develop resistance in other ways.
Exactly. Like they might just pump the analog out of the cell more efficiently.
Oh, sneaky.
That's why that final characterization step is so important.
Right, to make sure it's the real deal.
Exactly. We want to confirm true deregulation.
And sometimes finding the perfect concentration of the analog for selection can be a bit of a pain.
Yeah, it can take some fine-tuning.
So basically, analog resistance selection is this clever way to find those microbial rebels
Yeah,
that ignore the stop signs and just pump out valuable stuff.
exactly.
And by using these molecular imposters, scientists can identify the microbes that are ready to go into overdrive.
Ready for their industrial debut?
It's like microbial manipulation at its finest.
It really is a fascinating area of research.
But this idea of manipulating natural regulatory systems to get what we want, it makes me think, could we use this in other areas beyond just industrial biotechnology?
That's a great question to ponder.
Like, what about medicine or even agriculture?
There's a lot of potential there.
Definitely something to think about.
A lot of exciting possibilities.
Thanks for taking us on this deep dive.
My pleasure.
And for our listeners, keep those questions coming. We'll be back with another deep dive soon.
See you next time. Bye. Bye.